You ever see a self-driving car or maybe a drone and just wonder how? How does it actually see the world around it? Well, it's not magic. It's this brilliant combination of what you could call a software nervous system and a data crunching brain. So today we're going to pull back the curtain and see exactly how it all works. So that's the big question we're tackling. How does a robot actually see, think, and act all on its own? It really all comes down to two key pieces of technology, something called the Robot Operating System, or ROS, and a concept called sensor fusion. Here's how we're going to break it down. We'll start with the robot's nervous system, its software core. Then we'll get into how it makes sense of the world and dive into the three different levels of fusion that make that possible. After that, we'll peek under the hood at the clever algorithms creating certainty out of chaos. And finally, we'll see where all this incredible tech is already at work in the real world. All right, let's dive right in with that nervous system. For a huge number of the world's most advanced robots, that foundational system is called ROS, the Robot Operating System. Now, the first thing you gotta know is that ROS isn't an operating system like Windows or Mac OS. It's actually a meta operating system. You know, a better way to think of it is like a universal translator and a switchboard operator all rolled into one. It sits on top of a normal OS, usually Linux, and its whole job is to let all the different parts of a robot, the sensors, the motors, the cameras, the processors, talk to each other without any drama. To make this all feel a bit more real, let's meet our little guide for this section, TurtleSim. Yeah, it's a very simple simulator. It's just a turtle in a box, but it is absolutely perfect for showing how the complex parts of ROS work together in a way that's super easy to understand. We're going to make this little guy move. So, how does ROS pull this off? It's really built on four key ideas. First, you've got nodes. Think of these as tiny, focused programs that each do one specific job. Then you have the master, which is like a central phone book that helps all the nodes find each other. Nodes communicate over channels called topics, and the information they're sending back and forth, those are called messages. And check this out. This is what it looks like in action. That oval on the left, that's a node, a little program that's listening to my keyboard. The oval on the right is the TurtleSim node, which is running the actual simulation. So the keyboard node publishes movement commands onto that channel in the middle, the topic, and the Turtle Simulator node subscribes to that topic to get the commands in move. Simple as that. So this is really the key takeaway. ROS is that nervous system. It's this flexible software backbone that lets a robot's eyes talk to its legs, even if they were built by completely different teams. And this modular design is what makes modern robotics even possible. It lets developers build unbelievably complex machines out of simple, independent parts. Okay, so ROS is the nervous system, carrying all the signals. But what about the part that actually makes sense of all those signals? You know, what acts as the brain? Well, that's the challenge of perception. And the answer is a concept called sensor fusion. See, here's the thing. A robot can't rely on just one sense, because every single sensor has a blind spot. A camera is fantastic for reading signs, but it's basically useless in heavy fog. Radar can cut right through that fog, no problem, but the picture it gets is pretty low res. LiDAR creates these amazing 3D maps, but it can get totally confused by rain or a shiny black car. And your GPS? It's great until you go into a tunnel. The only real solution is to use all of them together. And this quote just nails the whole idea. The goal is to take all those different measurements and, I love this phrase, estimate or infer a single, much more reliable picture of what's really going on than any one of those sensors could ever provide by itself. So, to put it simply, sensor fusion is the robot's brain. It's the process that takes all this noisy, incomplete, sometimes even contradictory data from all the different senses and fuses it into one single, unified picture of the world that's way more accurate and reliable than the sum of its parts. But here's where it gets interesting. This whole fusion process isn't just one single step. It can actually happen at three different levels of complexity, from crunching raw signals all the way up to making high-level abstract decisions. At the very bottom, you have data-level fusion, where you're literally combining the raw data streams right from the sensors. One step up is feature-level fusion. This is where the system first pulls out key features, like, say, the edge of a lane from a camera or the corner of a building from LiDAR, and then it fuses those features together. And then at the very top, you have decision-level fusion. This is where each sensor system comes to its own conclusion. I think I see a car, I see a pedestrian, and then a final decision is made by weighing all of those individual conclusions. So how does a computer actually do this? How does it fuse all this data and turn a messy fire hose of sensor readings into a confident understanding of the world? Well, a huge part of the answer lies in some very clever algorithms. especially something called filtering. And one of the most famous tools for this job, an absolute legend in the field, is the Kalman filter. It is a brilliant algorithm for tracking moving objects, like another car on the highway. And its genius is how it's constantly blending two different things: its own prediction of where the car should be based on physics, with the noisy, imperfect measurements it's actually getting from its sensors. The core idea behind it is this beautifully simple two-step loop. First, it predicts. Based on where the object was a millisecond ago, it makes an educated guess about where it will be in the next instant. Then, it gets a new measurement from a sensor, and it uses that new piece of information to update and correct its own prediction. And it just does this over and over and over again, dozens or even hundreds of times a second. This constant predict and update cycle is what lets it filter out all the noise and jitters from the sensors and converge on a really stable, confident estimate of where that object truly is and where it's going. It's literally creating certainty out of uncertainty. So we've explored the nervous system of ROS and the brain of sensor fusion. Let's bring it all home now and look at where this powerful combination is already changing our world. And this technology is absolutely everywhere. You see it in the obvious places, of course, like self-driving cars and autonomous drones, but it's also powering the robots that navigate massive warehouses, it's enabling ultra-precise industrial automation, and it's even enhancing medical imaging and the augmented reality apps right on your phone. Remember our little turtle from the beginning? It followed a simple path because of commands sent over a ROS topic. Well, a self-driving car is doing the exact same thing, just on an exponentially more complex scale. It's fusing data from its cameras, LiDAR, and radar to build a model of the world. And then its motion planning node is publishing commands to the nodes that control the actual steering and acceleration. It's the same principle. So if there's one big idea to walk away with, it's this. ROS provides the essential framework. That's the nervous system connecting everything together. And sensor fusion provides the intelligence. That's the brain, creating a clear understanding from a messy reality. And together, they are the foundation for the autonomous systems that are truly changing our world. These systems are getting smarter every single day. But that leaves us with a final, massive question. Beyond just seeing and reacting, what's the next great challenge? How do we teach a robot to truly understand the context, the intent, and all the nuance of our complex human world?